of the day, there is a parallel session 2 as well going on. So this session will be chaired by Rumugam Thamijavel. And so Thamij, before I hand over to you, the invited talks are 30 minutes, 25 plus 5. You can give a warning at around 20. And for the oral presentation, it is 13 plus 2. You can give a warning around 10 minutes. Okay, over to you, Thamij.
Thank you, Prasad. Good evening to everyone. I once again welcome you for the final session of the second day proceedings of QMAT 2021. There will be 3 invited talks now. The first talk will be given by Professor Dhanvir Singh Rana from IISER Bhopal. So he's going to talk on terahertz probes for quasiparticle electrodynamics in complex oxides. So Dhanvir, are you there? Dhanvir?
Dhanvir, are you around?
Yeah. Sorry, I'm sorry. Hello, can you hear me?
Yes.
Perfect.
We can hear you loud and clear.
Okay, thank you.
You can start sharing your screen. Okay, then you have 20. I will just give you a warning around 20 minutes. So actually 25 plus 5. I will give you a warning at 20 minutes so that you can finish your talk in the next 5 minutes. And so, yeah, proceed.
Okay, thank you, Professor Thamilvel, Professor Pratap, and other organizers. Please excuse me, I can't switch on my camera because I'm sitting in some remote place in Himachal. So the bandwidth is limited, and then I'm also not well, so I don't want to show my face. Please bear with me. Yeah, so in next 25 minutes, I'm going to talk about these some popular terahertz probes for quasi-particle dynamics in complex systems. In this talk about the complex oxides. Yeah, so although this technique is popular now, people are aware of it, but just for the sake of completeness, I would like to give a brief introduction about the terahertz region in electromagnetic spectrum. So this is a region where the electronics and photonic sources meet with a frequency range of 10 raised to 11 to 10 raised to 13 hertz in the energy range of say 1 to 30 milli-electron volt and the time scale of 10 raised to minus 11 to 10 raised to minus 13 seconds, wave numbers around 1 to 300 wave numbers. That's where the spectroscopy works, and because of its popularity across disciplines in physical sciences, chemistry, biological sciences, and other civil and defense purposes, the application that it could show, it gained quite popularity in last 1 decade. However, I'm interested here only in condensed matter systems. I'll speak about 2 popular techniques that we implement on complex oxides. One is the terahertz time-domain spectroscopy with control of temperature and magnetic field, because the phase transitions that we see in complex systems are mostly induced by the temperature or the magnetic field as external controls. And optical pump terahertz probe, where we put the system out of equilibrium and watch it relax using terahertz radiation. So yes, so these are the 2 spectroscopies, 2 probes that we'll implement on some selective systems. Yeah, so why terahertz time-domain spectroscopy? In transmission mode, where we measure both the amplitude and phase of all the frequency components, it yields a complex permittivity which do not need any Kramer-Kronig transformation. This is why this is popular, that we can directly get the information about the amplitude and the phase at all frequency components. And then it helps us extract the dynamic conductivity, dielectric constant, and the magnetic permeability, which are the basic aspects of all the electronic and basic properties, which reflect the basic properties of all the electronic and magnetic systems. And of course, it probes all the quasi-particles which are because of either the bond carriers or the free carriers or the magnetic outer lattice and other things, other new exotic things which have evolved in the last few years. In time-resolved spectroscopy, yes, what it does is that it helps us realize the ultra-fast photo control of these phases. The time-resolved part could be because of two things. One is when we pump the system using IR radiation, or we pump the system using terahertz radiation and probe using terahertz radiation as well. Both have different aspects, and they help us extract the nonlinear properties, which is relevant in heterostructures and the interfaces, two-dimensional interfaces and superconductors and so on. While terahertz, optical terahertz pump terahertz IR probe is relevant in antiferrospintonics. If you see across all the condensed matter systems, the terahertz has almost served almost every sub area in the condensed matter system: semiconductors or the correlated metals, oxides, organic systems, topological materials, two-dimensional systems. As we see here, that in the range of, say, if seen in terms of wave numbers, 1 to 300 wave numbers, there are very many phenomena that lie in this energy range, which is why it has become kind of indispensable to explore certain aspects that the conventional technologies, the conventional tools cannot. In this talk, as I'm going to talk transition metal oxides, and the transition metal oxides, because in the last 3 decades, as we know, that starting from the superconductivity to magnetoresistive materials to magnetoelectrics, multiferrics, some exotic magnetic oxides, it has come down to a stage where the quantum materials are also part of transition metal oxides. So this area is defined by the computation between two fundamental energetics, the correlations, which are dominated, which dominate the 3D transition metal oxides. And as we go from 3D to 5D transition metal oxides, the spin orbit coupling interactions, they also become compatible with the energetics of electron-electron interactions. And because of this competition between two and their interactions, it results in some kind of very interesting topological phases. And terahertz spectroscopy has been able to probe both the phases evolving because of electron-electron correlations, interactions, and because of the spin orbit coupling. So yeah, I mean, as it covers almost, it has probed all kind of Fermi, non-Fermi liquid materials. It has resolved several fundamental phenomena related to metal insulator transition. It has served superconductivity, the field of magnetism, and recently there are very many studies where terahertz has given sufficient new insights into topological materials as well. So here, if I give an overview of the kind of quasi-particle phenomena that has been covered in complex metal oxides, is just a minute, there's something that appears here. Let me get rid of it. Yeah, so what we have seen recently in last 1 decade is that terahertz spectroscopy can explore the charge density waves, the polarions, the superconducting gap. It has also it also serves the physics of Cooper pairs, magnons in magnetic materials. And one of the very exciting phenomena that it has been able to unravel is the existence of magnetic monopoles, electromagnons in magnetoelectric materials, phonon polaritones in semiconductors, and recently this topological quasi-particles, Weil and Dirac kind of materials. They're also being explored quite intensively by terahertz tools. Okay, so I'm going to talk about certain things that we have unraveled in last 3-4 years. That is some phases in rare earth nuclides which were not unraveled by other techniques. First of them is the charge density wave type of excitations. And then we showed that these rare earth nuclides, they are unique mass divergence type insulators. And not only that, because the insulator metal transition can be tuned using epitaxial means. The sharpness as well as the transition temperature, they can be used as in turn in terahertz technology as terahertz transmission modulators. It also unraveled the non-Fermi liquid behavior of some rare earth nucleates, and we also explored the dominant control of the quench disorder in this class of systems. So if we see the phase diagram of these rare earth nucleates, one sees that as we go from lanthanum nucleate towards the heavy rare earth nucleate side, we see that the lanthanum nucleate compound doesn't exhibit any insulator metal transition, but for the all remaining systems starting from PrNiO3 to NdNiO3, which exhibit concomitant insulator metal transition to antiferro order, all other systems, they exhibit both the transition, but of course, starting from samarium down to lutetium, the transitions, they don't occur at the same temperature. So beyond that, there's not much known the origin of these ordered phases, why we get the insulator metal transition, which is concomitant with the magnetic transition, and if there's any underlying phenomena that is a different ground state than what appears from this phase diagram. And during this progress in these studies, it was also established that the magnetic transition, insulator metal transition, they can control by epitaxial strain, pressure, chemical doping, and so on, as is known for other oxides as well. So what was exciting for us to know about this phase diagram is that as per this Landau theory, the antiferro ground state was suggested to be a nested spin density wave, which has which induces a charge order or the charge density wave as a secondary effect. And this charge density wave, CdW, is proportional, the strength of the CdW is proportional to the degree of orthorhombic distortion. So which means that it has structural constraints. If we could show this CdW existing in the orthorhombic distorted systems, that means this theory is correct. And on the other hand, if we could produce samples which are not orthorhombic and we show the absence of this CdW in those systems, then this theory is correct. But however, before this study, there was no suggestion of charge density wave or spin density wave as the ground state of this system. So what we did is, and other than that, of course, the ground state and the role of disorder in this systems was not known. So what we did is, we tried to make samples. We took this prototype system, NdNiO3, which is the most studied system. And in this system, we took the template substrate in 3 different major directions, 100, 110, and 111 oriented substrates. And we deposited these films on the substrates with different orthorhombic distortions. All the films on 110 and 111 were orthorhombically distorted, while on 100 they were tetragonal. Terahertz spectroscopic studies were performed, and what we observed is that in 100, which is films which are not orthorhombically distorted, we see that the conductivity spectrum is featureless. It shows kind of clearly Drude kind of behavior, while in 110 and 111 oriented films, we see manifestation of a peak, which is very strong at low temperatures, and it weakens, and around the insulator metal transition, it disappears in both the systems. We saw the dispersion relation between the conductivity and the dielectric constant of these peak-like structures, and it shows a clear dispersion over here. And one could also see this dispersion in the spectral weight. So this clearly shows that the orthorhombic distorted samples, orthorhombic distorted films, they exhibit charge density wave kind of phenomena, while the tetragonal distorted film, they show clear featureless spectrum, which is consistent with the Drude behavior. We did some analysis, so the terahertz conductivity can be evaluated in the scope of this 4 model: the Drude model, the Drude-Smith model, the Lorentz model, and the extended Drude model. As per Drude model, the conductivity is defined by the scattering of the carriers. And as per this model, the conductivity spectrum should behave like this one as a function of frequency. the Drude-Smith model, it was modified, it's a phenomenological model. It was modified to incorporate the presence of disorder which results in the backscattering of the carriers, and that's defined by this quantity Cn. Cn ranges from 0 to 1. When it's 0, it's a Drude model. When it's 1, it has the maximum disorder, and it shows the shift of the spectral weight from zero frequency to some finite frequency, for example, as is indicated by this blue curve. Lorentz model is for the collective excitations such as charge density waves or the magnons, electromagnons, all kind of excitations. The extended Drude model, it takes into account the frequency dependence of mass and scattering rate. For example, one we have over here. So in the scope of these four models, all the connectivity of all kind of samples can be defined. So we evaluated our samples, for example, NDNIO3, in which we had this CW kind of peak, and one in which it was a featureless conductivity. So we extracted both the Drude part of conductivity and the Lorentz part of conductivity, and the other one in which we don't have any CW transition. We see that this is clearly our Drude kind of conductivity. We evaluate the scattering, the fission, and the CWs because of the fission scattering, because that's the energy range in which the fission scattering occurs. And we found that the scattering rate follows T-square law up to the transition. Beyond the transition, it diverges. So these were clear signatures that were consistent with the theoretical propositions. And this is what it sums it up over here, that as we go from a cubic structure to a highest orthorhombical distorted structure, we see the evolution of peak, and it strengthens as the orthorhombic distortion increases. So yeah, so what we conclude now is that the CW is a ground state of the charge of the rare earth nucleates, and which evolves with the orthorhombic distortion. Now, yeah, the second point that I would like to emphasize over here, and I'll come back again to the effect of the disorder on the charge density waves as well. But first, the effect of disorder has to be demonstrated in the system which do not exhibit any insulator metal transition. For example, NDNIO3 films on 100, in which we don't see any CW, but it has a Drude kind of behavior. So in the first one, NDNIO3, what we see is that the peak is at the lowest possible frequency, but this spectral weight shifts to higher energy when we go from NDNIO3 to a system which, as per tolerance factor, is same, but it has two cations with very large difference in their sizes. So yeah, so this is as per this model, we could also show that the terahertz anomalies could also directly relate to the oxygen deficiencies in these films, because there's a way to measure the conductivity, correlate the conductivity with the oxygen deficiencies. So this was another way of correlating the defects with the dynamic conductivity. Now, how could we correlate this, the defects or the disorder with the charge density wave? So we took a system. This is not a slightly different system now, SMNI3, because we have to show that the CW occurs across different systems. So yeah, this is known that in SMNIO3, the oxygen non-stoichiometry can be induced by tensile strain, and that can also be induced by the thin film, by varying the thin film thickness. So there were some studies which had already proved this thing. We just took this template and formed these three films with the different thicknesses, and we could show that as per change in the lattice constant, and that they were coherently strained, that there were oxygen deficiencies, and the oxygen deficiencies are maximum in the least in the thinnest film, and the oxygen deficiencies, they decrease as we go on from 25 to 110 nanometer. Now, as we show here, if we go from left to right, all of them are coherently strained, film quality is good and all that. What we see over here is that in these films where the thickness is low, the defect density is large, the manifestation of two peaks, peak A and peak B. Peak A is the pinned mode and peak B is the bond mode, because as per theory of the Friedel oscillations, the bond mode, if there's large number of impurity present in the system, would interact with the impurities as well, because there's a spatial oscillation around the bond mode, and that bond mode, the phase difference of the spatial oscillations of the bond mode and pin mode is different, and hence it results in the formation of another mode, that is this mode. Now this should appear as the number of density should decrease as we go from 25 via 65 nanometer to 100 nanometer. We see that this peak almost disappears. Not only this, even this peak also disappears as we go. Of course, we can't say anything about this because it goes towards higher frequency side, which is not accessible to a spectrometer. However, the point is that the effect of disorder was clear. As the disorder decreased, the number of defect densities decreased, the bond mode disappeared. So yeah, so this was another thing that we could prove till now, that the charge density wave is the ground state of the rare earth nickelates, and there's a definite effect of the disorder on all kind of low energy phases. We also showed that when the system is dissolved from an insulator metal transition by the application of epitaxial strain to a completely metallic state, there's a transition from a Fermi liquid behavior to non-Fermi liquid behavior. Of course, we didn't show it; we just followed a study. But there was, of course, a question on that we could say it for certain only when this rule also this is also reflected in the frequency dependent studies, that if the scattering rate doesn't follow the t square, it should also not follow the frequency square. So our Terahertz frequency dependent conductivity study confirmed that the conductivity is not proportional to square of the frequency. Hence, it is indeed a non-Fermi liquid system. As I said that, hello, I can't hear. I think
you have 5 more minutes.
Okay, thank you very much. So it's 20 minutes or 25 minutes are over?
25 minutes.
25 minutes are over, right?
Sorry, 20 minutes are over. Sorry.
Okay,
yeah.
Thank you very much.
5 more minutes,
okay. Yeah. Okay. Yeah. So in the beginning, I mentioned that the insulator metal transitions, because we are able to tune the insulator metal transition, we should be able to use them as Terahertz transmission modulator. And this is a demonstration over here that samples with varying strength or varying robustness of insulator metal transition are able to give us transmission, say from 1 to 0.4. And these insulator metal transition can be tuned to room temperature by just changing the tolerance factor. So just by being able to change, vary the temperature, say in the range of 20 to 30 degrees, we'll be able to vary the transmission of the terahertz radiation by 70%, 60 to 70%, because there are systems in which the intensity dependent studies have been proposed. So this is one application of insulator metal transition which can be tuned using epitaxial strain engineering, that we will be able to implement the rare earth nickelates as terahertz transmission modulators. Now, next 5 minutes or 4 or 5 minutes, I'm going to talk about the time resolved part, in which will show that there's strong electron phonon coupling by the means of evidence of acoustophonon coupling, the existence of acoustic phonons in nickelates. So yeah, this is typical time scales of some basic interactions. One that I'm interested over here is in the time scale of 10 raised to minus 12 seconds. So there are two phenomena, those are interesting. One is the spin precision in the antiferro systems, that is 1 to 100 picoseconds. And another is the spin phonon coupling. On this side, if you see, then we have electron acoustic phonon coupling. So these are three phenomena that can be unraveled by optical pump and terahertz probe studies. So what we do is that we take the femtosecond laser pulse and push the system out of equilibrium, and then terahertz probe, terahertz probe, it probes the relaxation and excitation dynamics. So there are three systems that we've taken over here. One which doesn't exhibit any insulator metal transition, for example, EU and IU3 at room temperature, and LNIU3, which is completely metallic system, and one intermediate system in which, of course, it does exhibit insulator metal transition, but it's a bad system with very low conductivity. So what we say is that EU and IU3, what we say is on once the femtosecond laser pulse is incident onto the system, the terahertz transmission decreases because we have free carriers now, and the system relaxes as per bi-exponential theory. In LNIU3, because now we are disordering the carriers, the transmission decreases. What we say is that the LANIU3 and LA25EU and IU3, there are two things which are common over here. That is the evolution of a peak over here, B peak over here and over here. So what is it? Because if it has to relax exponentially, we shouldn't see this peak. So this is because in this system, the strong electron phonon coupling. So what happens is that once the system is pumped by say 800 nanometer pulses, which are our band gap pulses, it excites the carriers. They go to the conduction band. They have very large energy. The temperature goes very high. Once they interact with the lattice, then electron phonon thermalization takes place. The lattice expands and it emits the acoustic phonons. So this is possible only when there is a strong electron phonon coupling, the emission of the acousto-optic phonon. This is not a very common phenomenon in most of the systems. This is the only system along with V2O3, which also is a canonically similar system where we could show the emission of acousto-optic phonons upon illumination of the system by ultra-fast pulses. So what are the implications of this demonstration? Like we have this surface acoustic wave device in which we have an input transducer and output transducer in which the strain is induced by some mechanical means, and that it's converted into output transducer and some electrical signal is achieved. In this case too, it induces some mechanical strain. The femtosecond laser pulse, it induces some mechanical strain. So this mechanical strain, which appears in the form of the acoustic strain, can again be detected by the output transducer. Using the femtosecond laser pulses of different frequency, intensity would have a different strain induced into that. So this saw can be replaced. Of course, we need some more demonstration with different kind of different wavelength of radiation and different intensity. But there's a definite possibility that this device can be replaced by ultra fast by rare earth nuclides illuminated by the ultra fast femtosecond laser pulses. So I conclude here that the time averaged and time resolved spectroscopy has now become indispensable to probe the low energy ground states and the interactions among fundamental entities. We showed the CW type excitation, the structure control, and in turn, we also showed that the insulator metal transition can be used as terahertz transmission modulator. Thank you very much. Hope I was within time.
Yeah, thank you. Thank you very much, Dhanvir Singh Rana. So the talk is now open for any discussion, questions, comments. You can unmute yourself and you can ask your question. So before somebody asks any question, let me, Shovan, you want to ask a question?
Maybe you can proceed and then I will ask.
Yeah,
Go
sure.
ahead.
So you were talking about the substrate for this NDNiO3, which are oriented along 100, 111 and all these things, no? And depending on the orientation, your NDNiO3 grows in a particular crystallographic orientations or crystallographic structure.
Yeah. So it's the template. If the substrate is 110.
What is the substrate that you are using here?
This is a terahertz transparent LALO3 substrate, LAO.
Okay.
So we have to be careful the substrates. Generally, we don't use ST, which is very popular one because there will be no transmission. It's a dielectric system, so it absorbs everything. Yeah. So yeah, all the epitaxial films, if I say the substrate is 100, the films will be 100 oriented. If it is 110, 111, the films will be in the same direction. Yeah.
So this rare earth does not order magnetically here?
No, it's anti-ferro system.
This is due to nickel or? That is due to nickel, isn't it?
Yeah, it's because of nickel.
But rare earth, I'm asking about rare earth.
No, rare earth, nobody has found any evidence of
Okay.
ordering of rare in these systems yet. Yeah.
Okay, Shovan, you
Yeah.
can ask your question. Yeah.
Thanks. So Dhanvir, that was a really nice talk. I have one question regarding the last part where you showed your pump probe measurements, this optical pump and terahertz probe. You showed about 2 samples where one, the transmission change was negative, and in the other case, the transmission change was positive. Yeah, indeed, here. For example, in ENO and LNO, there is a flip of sign. What does this basically mean here?
So ENO3 is an insulating system.
Mm-hmm.
So when you use the above band gap pulses, it becomes metallic. The other one is a metallic system. So you disorder the carriers.
Okay. Okay. And the other thing is that I see kind of 2 relaxation times in this, right? So if you see, so one is a very fast relaxation just after the excitation.
Yes. Fast and slow relaxation times. Yeah.
So here, do you assist it to only phonons, or you would also have some electronic relaxation in the first part of the?
I mean, see, Shovan, all these studies were done only at room temperature. We are extending it to low temperatures. I won't be really able to, I mean, we also have this question in mind, what you asked me. But unless we do these studies in 2 different phases of the same system, I won't be able to answer this question as of now.
Okay.
Right now, these are like different phases in different systems, not like different phases in one system. I have to see across the transition in the same system to be able to answer this question.
Okay. Okay, good. Thank you.
Okay, Dhanvir, there is a question in the chat box. So here they have Dr. C. Dhanashekhar has asked a question. What is the effect of magnetic field on the CDW type excitations seen in terahertz?
So in this, so we have seen, we have seen this effect of magnetic field both in manganites and nickelates. In manganites, we see that the CW becomes weaker. That's our recent studies. In nickelates, there's no effect of magnetic field on the CW because there's no connection, in fact, because we are unable to disturb the antiferrous system with the kind of magnetic field that we have in our system. We don't have anything more than 6 Tesla. 6 Tesla hardly does anything to the, the magnetic order, antiferro order to the system. Unless we are able to break the antiferro order, we won't see any difference. That's my presumption though, but that's how it looks like. We didn't see any effect in a field up to 6 Tesla.
Okay. Can I ask something here? Sorry. Of course, sure. Can I just ask?
Yeah. Please, both go ahead. Ask question. Yeah.
Very nice talk, Dhanvir.
Please go.
So what is this in this? Yeah, just sticking to this transparency. So what is the sort of the minimum pump power you need to sort of induce a change? Or say pump fluence, what is the minimum pump fluence you would need to induce a change?
So it's written there in this case, I mean, I think 0.5
squared. I was just wondering.
Yeah, it's a lot of power required basically.
So nanojoules, nothing will happen, is it?
No, nothing. You need amplifier laser for this.
Okay, so otherwise nothing really happens.
Yeah.
All right. If there are no more questions, let's thank Dhanvir Singh Rana. And thank you, Dr. Dhanvir Singh Rana.
Thank you very much.
Next, we will proceed to the next talk. Next is again an invited talk by Dr. Shovan Pal from NISER. He'll be talking on scrutinizing microscopy of terahertz nonlinearities from ferroelectrics to quantum cascade structures. Yeah, Shovan Pal, it's all yours. Yeah. You are muted. Shovan, you are muted.
Yeah, can you hear me now?
Yes.
So can you share my see my screen?
Yeah, sure. We can see your screen. Put it in the slide. So yeah. So you have 20 minutes too. At 20 minutes, I'll give a warning, and then you have 5 more minutes after that.
Yeah. Thanks, Arumugam, for this very nice introduction. And I would first like to thank all the organizers for hosting this wonderful conference in these times and giving me an opportunity to share my very recent work on something that I call as terahertz nonlinearities and looking into the in-depth, the microscopic, mechanisms of what actually gives such nonlinear signals. So to be honest, given the time constraint, I might only be able to look at the ferroelectrics, and maybe for quantum cascade, we might have to see another time. Okay, so let me get my pointer. Okay, great. So before I go ahead, let me quickly acknowledge all my collaborators. So basically all my people from my past affiliation from Department of Materials in ETH Zurich, with all the collaborators that I worked with, and in particular from Max Born Institute for Nonlinear Optics, Professor Rana, who actually developed and gave us a very nice understanding of what actually is happening when we are looking at this nonlinear physics. From the cascade laser part, we had a wonderful collaboration with the group of Jerome Feist, but as I mentioned, I might not be able to go into the topic. For the funding, we had really a lot of support from ETH, from Swiss National Foundation, from DFG, and from the ERC funding sources. Now, let me come to something, the core of these studies in the nonlinear kind of nonlinear physics, which at the heart lies something that we call as correlation. And the very word correlation comes from actually two words, which is kind of con relatio, and that means with relation. And if you just think a bit in the mathematical terms, so you have something like two quantities, let's say A and B, which if you say that they are correlated, and then if you want to measure this quantity simultaneously, and if you measure them in separate measurements, like individually, then you would see that this doesn't equate to each other, which means there might be some additional terms that would be required to bring this inequality sign to equality. So that is basically what correlation actually means when we talk about in the physics world. Now, it's not just in the condensed matter science, so condensed matter and material science, they host a lot of compounds, but it's not just limited to those. We do have a lot of correlated systems in the other side of the scientific world, that is the chemistry and the biology, onto the other side, which is actually the geoscience. The very core of the entire planet is basically a very strongly correlated systems, and so understanding correlation is in fact one of the prime topic in the modern research today in condensed matter, and not just condensed matter, in the entire scientific community. Now, when we talk about correlation, and we would like to see correlations or coherences among the different correlations, so we would, there are different ways of looking at it, and the typical way that I would be talking today would be something that I call as two-dimensional spectroscopy. And in particular, this is actually systems where low energy excitations are more relevant. So we would talk about two-dimensional terahertz spectroscopy. Now, drawing a quick kind of analogy to this mathematical expression that we have. So in a two-dimensional spectroscopy, what we would do is we would study a system of interest using 2 terahertz pulses, and that's where this 2-dimension comes. So 2 terahertz pulses, I call it a pulse A and a pulse B, and then I would individually look at the system using these 2 pulses, individually with pulse A and pulse B, and then I will bring both the pulses together into the system and I look at what is happening. And of course, if the system has completely, or if the system is boring and if it doesn't have any form of nonlinearities or any kind of correlations, then you would definitely have this already as equal. But most of the cases you won't, and you would end up with something called this nonlinear contributions. And you can simply obtain this by subtracting the scenario where you measure the system with both the pulses, and subtract these quantities where you measure the systems with individual pulses. So that is basically the heart of the entire study. Now, when we talk about correlated systems, the very system that comes to our mind is quantum material, and that is basically the theme of this conference, in fact. So the typical quantum materials that we are always dealing with are classified as the strongly correlated systems, and ideally the systems where you have a lot of charge, spin, lattice, orbital, degrees of freedom, and each of them in some way or the other are talking to each other, and you have to take into account all these interactions, which makes the system complicated and yet very fun to look at. One of the system which is very favorite to me is basically this nickel oxide system, which actually is an antiferromagnetic system. And in this beautiful work, they showed that upon excitation with a terahertz pulse, for example, you see here the magnetic field component of the terahertz pulse. If you pump it, you can in fact initiate something called a spin wave in this material, which comes out as these oscillations that correspond to this 1 terahertz spin resonance. So you see that using a terahertz pulse, you can actually excite a collective motion of spins, which is the spin wave motion. In yet a very recent work, which was done in the group of Cavalieri, they found that one can actually introduce something called photo-induced superconductivity, which is done on K3C60 material, where they actually pumped a system with the terahertz light, and they saw that there is a photo-enhanced conductivity in the first few picosecond of the system, and that eventually actually relaxes to the thermal state, which is shown here by the red curve in terms of the conductivity or the reflectivity values. So that relaxes over longer times, but just after the excitation in the very close time, it is actually having a lot of photo-induced contribution to the superconducting state in this material. And not just that, what is even fancy is that such a phenomena lasts over a pretty long time. I mean, 4 picosecond is quite a long time that this photo-induced superconductivity can actually stay there. And what is even more fancy is that the measurements were performed at much higher temperature, like 100 Kelvin, which is where the superconducting temperature here is only 20 Kelvin for this material. So by light-induced pulses, you can in fact enhance the superconducting nature in the systems. So these are some of the advantages of looking into the system using a strong light field and fields with frequency components in this low energy excitation. Now, as Professor Rana mentioned, it is not just one simple or two small examples, but there are a plethora of phenomena, as he has rightfully mentioned, that one can look at in different kinds of materials. And you can see that one additional part here is this heavy fermion system that we also have investigated in a very nice, in a very deep manner, that also falls into this terahertz range, in this beautiful range of the compound of this spectrum. And in my talk today, I'm going to actually address one of these very fancy phenomena, collective motion of lattice movements, that is called this phonons. In particular, what I'm interested in is this soft phonon mode. Now, why do I actually want to look at this nonlinearities of the so-called soft mode? It's just a lattice mode, which becomes soft when you approach the phase transition. Now, the interesting part about the nonlinearities is that which came across this bunch of works in 2019, where by introducing a terahertz pulse, one can actually bring in a quantum paraelectric phase. One can bring in ferroelectricity from a quantum paraelectric phase in this so-called strontium titanate compound, which is actually a ferroelectric compound at room temperature. Now, this has been seen also in a simultaneous work, which came out, as you can see from the volume number and the page number simultaneously, where they actually showed the enhancement of the polarization, which actually tells you that by pumping or by introducing or straining the material in an optical manner, you can introduce a transient ferroelectricity in the material, which is much higher than the usual kind of ferroelectricity that one can talk about. In another experiment, sometimes later in that year, there was another group with Stefano Bonetti and Martin Hoffman, where they showed that one can use something called phonon up conversion, where they can, by a nonlinear coupling, one can couple this soft mode to a much higher line in the frequency components to a transverse optic mode. Now, while these studies show that one can typically use or take advantage of this nonlinearity, something that you can also see here, the nonlinear coupling of the soft mode to do some really fancy physics, while the very thing about the nonlinearity is been studied quite a few years back in 2012 and earlier in 2017, where they showed that this nonlinear response, what they mean is actually upon introducing or exciting with the terahertz pulse, there is a blue shift of the mode, and something that I will explain in detail, something called photon echo signals or nonlinear signals. These are basically the nonlinearities that one talk about when we talk about the soft mode nonlinearities in the literature. One fancy thing about both this literature was that both these phenomena or both these signals were found at much lower electric field intensities of kilovolts per centimeter, whereas the earlier works in these cases were in the order of megavolts per centimeter they used. So well, one can already see that having such nonlinearities is already happening in the much lower or in the much smaller terahertz field intensities. So an obvious question to ask is then what actually is the origin of the very nonlinear response of the soft modes? So that is where we come in, and up until or prior to our work, there were a lot of things that were kind of not understood. So for example, based on this low field kind of nonlinearity, the open questions were, so given the fact we know that a soft mode is a hybrid mode, which is basically a combination of an electronic and an ionic motion. So what actually is the portion of the electronic motion compared to the ionic motion that actually survives or that is actually present in the soft mode quasi-particle? So we can find an answer to this question by looking at the linear response and working out actually the oscillator strengths of the corresponding contributions from the electronic and the ionic part. The second question that was left unanswered was which is actually the dominating soft mode nonlinearity. So basically, if you stroll around in the literature, you will find that there are a couple of theories, such as this enharmonic potential or enharmonicity from the ionic potential, or is it actually the charge density deformation that comes when you start moving an ion, the electronic cloud associated with that also moves. So is it the charge density deformation that actually dominates the soft mode nonlinearity? Well, one can actually see that by looking closely into the type of shift that one happens when you actually pump the system. So if you have a red shift, it would be actually the enharmonicity, whereas if you have the blue shift, it would correspond to the charge density deformation, the dominating soft mode nonlinearity. Now, one would also like to know what if we can provide an experimental evidence of something that we call as the local field contribution. And this is coming purely from the fact that the electronic cloud associated with the ionic motion, they are in fact coupled to each other, and one has to take into account this coupling. And we can actually look into this. We could actually do this by scrutinizing the nonlinear signals and in the time domain, in the time field profiles that I will be talking about. Now, the other question is, can we provide a theoretical model that gives a rather quantitative agreement with these experiments? Well, in this case, having our experiments confirmed, we came out with a hybrid model that actually shows that indeed there are quantitative agreements and not just qualitatively that we can show all these answers to. And for this, the usual kind of system that we took was a ferroelectric system. And in this case, we used a thin film system that we can easily strain tune it to bring mainly a couple of factors. Number one, we want to have a soft mode that would be our target for looking at all these answers. And that too, we would like to preferably have it at room temperature to avoid complications in the experiments. The other thing would be to look at the ferroelectric phase transition. So basically, we would like to have this strain tuning in a way that we are in this ferroelectric phase transition phase, such that the light pulse can easily change its transition from one phase to the other phase, or we are closely into this unstable point of the phase diagram. Now, for our system, what we did was we grew 50 nanometer thin strontium titanate thin films on a substrate, which is dysprosium scanded. We used the state-of-the-art pulse laser deposition technique to grow those. And we tried to tune or strain tune our STO films on the DSO such that the strain was around 99%. This was not an accident. This was purely based on the earlier studies, that if you have close to 1%, then you can actually at room temperature, you would be in this range of ferroelectric phase transition where you would like to locate yourself for going ahead and to study this nonlinearities of the soft mode in strontium titanate. Now, the ideal next question to answer would be, should we locate the soft mode? And that we did using our terahertz time domain spectroscopy. So what we essentially did was we looked at the transmission of the substrate and the film on the substrate. And this is what we figured out, that the soft mode is actually located around 1.17 terahertz, which is shown here by the shaded curve. And if you take the transmittance, you see a very nice kind of a resonance feature that from where you can also evaluate out the real and the imaginary component of the dielectric constant using the trivial relations that one can find from the literature. And to model this, we used a harmonic kind of an oscillator model where we used the ions, omega ions, which is coming from the soft mode, and the Z effective is the effective, the bond effective charges. And the reduced mass actually takes into account the entire movement of the positive ions, which is the strontium and the titanium, corresponding to the negative ions, which is the oxygen in the system. And it has a beautiful agreement because according to what you should expect, the real part has a zero crossing, and whereas the imaginary part has a very nice peak-like feature that corresponds to the soft mode resonance. So having located that, one would now like to look at the oscillator strengths from this. So we tried to evaluate this, and we found out that the oscillator strength corresponding to the ionic motion is very small compared to basically the electronic contribution that is there in the material. So if you take into account only the ionic contribution from the material without taking into account any electronic movement, you would end up with the oscillator strength of around 1 units. Whereas if you take into account the hybrid mode, you see that it's roughly in the order of 5 units, so which is basically a ratio of 5 times almost higher than the ionic contribution in the system. Well, this actually answers the first question, that is, in this material, one of the determinant role that plays in governing the nonlinearities would then indicate the electronic motions that is actually more predominant in this. So having got this, we would like to look for the nonlinearities or nonlinear signals. And for this, we employed this 2-dimensional terahertz time domain spectroscopy, and where we employed 2 different pulses. So one pulse that actually travels through a stage, which can be delayed with respect to the arrival of the other pulse on this generation crystals, which generates then 2 different terahertz pulses. And then these 2 pulses would then collinearly propagate through the sample, and then we will actually do the trivial electro-optic sampling using this femtosecond laser systems. Now, the first, as you remember, we would like to look at the response of the individual pulses, and then we would try to look at the response of the 2 pulses together. So let's say we look at the first pulse here. So this pulse, which is actually traveling through this stage, and then you can clearly imagine that as you are moving this pulse over the stage, then the corresponding sampling time would also change, and that would lead to this kind of a field profile for a 2-dimensional scan of terahertz pulse, which I call as pulse A. The other pulse, pulse B, as you can see, is not traveling over the stage, which is just traveling through without the stage. And then if you just measure or scan a pulse or take a scan with the function of this time delay, then you will not see any change, and this will be more or less at 0 time delay all the time. And this is basically the second pulse that one can look at. Now, when you bring both the pulses together, this is something that one would expect. And from that point onwards, if you just subtract the individual measurements that we took earlier, you can take out something called the nonlinear signal that you can clearly see is lying in this something called the causal range of the light matter interaction region of this 2-dimensional scan. Now, one can associate from here, one can go to the frequency domain and look at the different types of nonlinear signal. And to understand that, one can associate some frequency vectors associated with these 2 pulses, so pulse B and pulse A, the combination of which would then give you the different types of nonlinear signals. To be very fast, one can understand this as different types if you observe the signals at different points in the frequency space. So something like a combination of 2 components from pulse A and 1 component from pulse B would land you to a point in the frequency space, which is here. Or if you have 2 components from pulse B and 1 component from pulse A, you would land up to a position here. Likewise, you can have different other compositions, and you would land up to different frequency components. And each of these has a particular name. So basically, you see here, the phase of this pulse would cancel out each other. So basically, the pump pulse is eventually the A pulse, which goes away, and you are actually having the information of the B pulse only. So that is called as a probe. So these are the 2 types of pump probe signals. Whereas if you have the information of both the pulses with certain combination of the frequency vectors, you get something called the photon echoes up and down in the quadrants. So these are called Chi3 signals, because arriving at each of the signals, you need at least 3 pulse sequence here. Unlike the second harmonic signal, you can actually arrive at this point using a 2 pulse combination. So that is basically a second harmonic signal. So one can also arrive at this point in the frequency space. Now, to explain our experimental observation, what we did was we used this local field correction method, where we say that our ionic part is a perfect harmonic oscillator, and our electronic motion can be actually understood quantum mechanically as an ensemble of 2-level systems. And the 2 motions, in fact, are coupled to each other using this local field correction term, which is actually the second term in this expression. So the local field is actually a combination of your incident electric field. So this is the terahertz field, and this is basically the coupling term that couples the electronic motion with the ionic motion in there. And then the emitted field, the nonlinear field, can be written as this rate of change of polarization. The polarization current that one can have would eventually lead to different types of nonlinear signal. So this was a very simple model that we used. So in fact, that answers the question 4. So we do have a very simple model, a hybrid model, hybrid of the electronic and the ionic motion that can explain our nonlinear signals.
So once you have 5 more
yeah.
minutes, huh? You have 5 more minutes.
Yeah, okay. So I'll try to wrap up soon. So if you look at the nonlinear signals, if you take a two-dimensional Fourier transform, you end up with all those nonlinear signals that I mentioned in the frequency space earlier. And from the theoretical model, you can actually match very nicely all those signals that one can have. So basically the pump probe signals and the photon echo signals. One very distinct thing about this is that they are all separated in frequency. So one can eventually do a Gaussian filter, take out these individual signals, and then eventually look at the time profiles of these individual signals. And that's exactly what we did. The individual signals would have a very different kind of a time profile, and that's what I'm going to show you now. So if you take at the pump probe signals, so they will have a very different kind of the inverse Fourier transform of these signals would look very different compared to so this is a pump. So basically this is dominated by the probe pulse, which is the B here. And this is dominated by the A pulse, which is the probe pulse here. The phase of this pulse remain. Now the photon echoes would be then looking very similar, but in a very different way. So I will come back to this point a bit later. Let us first look at the pump probe signal. So if you now take a pump probe signal, let's say the B pump A probe, and you come at 2 different points, let's say at a very far point when the 2 pulses are well separated to each other, and at the point of interaction when both the pulses are together. So compared to these 2 scenarios, you have one case where the field is extremely high and where the field is half of the other part. And you can see that the time trace and the frequency Fourier transform shows a clear kind of a blue shift. So as you are close to the interaction point, which would be the lower time value, the blue curve, you see that there is a clear blue shift compared to the original location of the soft mode, which is at 1.17 terahertz. So this blue shift eventually tells you that the dominance of the electronic part, and that is this charge density deformation, that answers my question 2 in the case. Now, having this thing as a function of time, delay time, you can actually sample out the entire frequency space, and you can see how actually the frequency component is changing as a function of the pump probe delay. So when at the original case where we had a negative transmission, suddenly becomes a positive transmission over time. And this is just a phenomena where induced absorption is shifting to something called a bleaching in this case. Now, one can also take a look at the photon echo. Now, typically, it says that if you have a photon leading pulse, that is basically the first pulse arrival is pulse A, then you cannot have a scenario or signal which corresponds to the BAA signal. So long story short, in this kind of a scenario, in the ABB photon echo, you are not supposed to expect this signal at all in this case, provided that you do not have any, or you do not have any local field correction. So this has been theoretically verified. So if we turn off the local field correction or the coupling between the electronic and the ionic motion, you see that you should not have this. Whereas in our experiment, we clearly had signals in the acausal range. And that is purely because of the fact that once the pulse A goes away, it actually leaves behind something called this local field contribution, that is the derivative of this pulse, which can be prolonged tail. And that tail can always satisfy the relation, which is that the pulse A coming behind pulse B all the time, eventually leading you to this kind of a signal. So that means that there is a clear evidence of this local field contribution that answers my third questions and eventually all my questions, open questions that we had in this. So in short, what we saw is that the terahertz soft mode that we have is actually dominated by the electronic contributions in this hybrid quasiparticle, the lattice motion being just a perfect harmonic oscillator, and that can be only effective when you have a very, very high electric field, or you are at this slow thermal motion or slow thermal phase transition case. So with this, I come towards the end of my talk. So basically, to summarize, what I have shown you is that a very unique, a very different kind of a spectroscopy, which is this nonlinear spectroscopy with intense pulses, is in fact a very unique tool that can help you understand a lot of interesting physical phenomena at the very quantum level. And in this work, I have just shown you one example where we looked at the nonlinearities of a soft mode in a ferroelectric perovskite. And just to give you a flavor, this is not just it. One can actually use this system for different types of phenomena, be it a Kondo system, be it a superconductivity in K3C60, for example, or be it some exchange interactions in multiferroic compounds, such as in cupric oxide, or observation of Fermi. This is a very nice work where they use two-dimensional spectroscopy to look at the Fermi glass system and look at the Fermi glass behavior of this kind of a simple silicon substrate. To the point where they have also used such pulses to use to switch symmetry in an ultra-fast manner in something that we call as this wild semimetal. So in short, as Professor Rana also mentioned, a terahertz is in fact freaking awesome. Why don't we just light it up? With this, I thank you for your attention. Thank you.
Thank you. Thank you very much for the wonderful talk, Dr. Shovan. So now if there are any questions, yeah, there is a question by Priya Mahadevan. She has already risen her hand. Priya, you can go ahead.
Yeah, okay. Very nice talk, Shovan. Can you hear me?
Thank you. Yes,
yes.
Yeah. So, I mean, I just had a naive question with your conclusion. So you're saying, I mean, with respect to your shift, your conclusion is that essentially it is the, what do you call it, your charge density deformation, which is dominating this thing.
The nonlinear
isn't the charge density the nonlinear behavior, but isn't your, isn't that arising because of your ionic motion?
Yes, I totally agree with you. So see, when I say that it's dominated, I'm not saying that the ionic motion is not there. I'm saying that it's there, but when we are looking at light-induced nonlinearities, which typically the earlier works from Cavalieri and Peter Armitage and all of them looked at. So when you are coming in with an ultra-short pulse and when you are exciting the sample within a picosecond, within a single cycle pulse, and you are looking at all these nonlinear signals, then this particular nonlinearity, the way these nonlinear signals would follow, that is determined by the electronic motion, because that is the only part of the entire system that can be fast moving, moving in line with the pulse. Whereas ionic motion, that is there, that is always there, that brings in the so-called enharmonic potentials, and that is relevant when you are coming with very intense pulse in the case of megavolts per centimeter, or even to be more specific, when you are talking about a thermal phase transition, there the ionic motions do play a role. But in the light-induced phase transition, it is predominantly governed by the electronic contributions in this quasi-particle. So that is what I'm saying.
Okay.
Did I answer you?
Okay, thank you. Yeah, kind of. So can I ask a follow-up? I mean, in the sense, it's a very naive thing, follow-up. So essentially, you're saying that the ionic motion happens,
yes,
and or maybe it comes back, but the charge density hasn't come back in the same time scale or something like that. A decoupling of the
ionic
two.
motion ionic motion has happened. You have to take that into account. But then when you are taking a look at the nonlinearities, you have to consider, you cannot just take, so what I'm telling you in a more general way is, do not forget that there are electrons there. So that is there, and you cannot also take the entire electronic response as more like an average thing. So when you solve, you have to solve the electronic part simultaneously to actually match the nonlinearities that you get. In particular, the presence of the photon echo. This is simply not possible if you are just working with the ions. You will never land up here. So in order to come here, you have to take into account, simultaneously solve the electronic equations of motion along with the ionic equations of motion, and not just take the electronic picture as an average and add it at the end. So this is, if you understand, this is what I mean.
Okay, thank you.
Yeah, we are already on time now. Thank you, Dr. Shovan, for a very nice talk.
Yeah.
Okay. The next talk is by Dr. Mayukh Mazumdar from Shiv Nadar University. He'll be talking on the evidence of spin liquid behavior in the extended quantum critical regime of pressurized cerium palladium aluminum. So,
okay, let me just share the screen.
Yes.
Okay, is my slide is visible?
Yes, yes, yes.
Okay, in full screen, right?
Yes.
Okay. Okay, yeah. First of all, thank you very much for giving me the opportunity to present my very recent research work at this nice conference that has been kind of going on for the last 3-4 years. Great initiative, definitely. So, yeah, as you can see from the title, I mean, the title that I have given there is more elaborative, but now while talking, I think it is better to give you a more general kind of title. So the title, as you can see here, Order at the Border. So I'll be talking about a particular system that is cerium palladium aluminum. What happens to this system if you pressurize the system? So what do I mean by order at the border? To understand that, let me just proceed with the next slide, by which you can understand what did I mean by order at the border. So before going to the details, let me just tell you in a very basic thing that what happens if you have a second order classical magnetic phase transitions. So we know that at high temperature, you have dominating thermal fluctuations. But what happens in the magnetic systems that at low temperature, the exchange interaction between the electrons wins over the thermal fluctuations, and the system goes to a long range magnetically ordered state. And the temperature at which the winning of this exchange interaction happens over the thermal fluctuations is called the classical critical point. And we know that just above the classical critical point, we have some critical region. And within this critical region, and we know that all the physical properties, as for example, the specific heat, susceptibility, relaxation rate, all these things diverges towards the ordering temperature. And theoretically, as well as experimentally, it has been found out that all these parameters show some kind of power law type of behavior. And the exponents are already been theoretically proposed to be. And the other thing is that these exponents are actually going to tell you what kind of system this particular system is. And this is some kind of a universality class, even though you do not know the microscopic details, but still you can, from that particular exponent, you can get an idea about the nature of the system itself. So this is what happens for a classical second order magnetic phase transition. So now let us move forward to the situation where you have quantum criticality, or rather quantum critical phase transition. So in the similar way, if you can see in the right hand side figure, that you have, let's suppose with a system which has a long range magnetic ordering at a finite temperature, and with some external quantum critical tuning parameter, it can be, it must not be temperature, but something else, which means it can be the pressure or the magnetic field. With the application of pressure or magnetic field, if you are able to suppress down the ordering down to t equal to 0, then at that point is known as the quantum critical point. So now you see that is the point where the system is at the order at the border. Below than that, you have the order state. Higher than that, you have the non-order state. And around that quantum critical point, you see a lot of quantum critical fluctuations. Similar like in case of a classical second order magnetic phase transition, where you have these critical fluctuations driven by thermal fluctuations. On the contrary, in this case, you have the quantum critical fluctuations that is actually kind of will be very much effective around that quantum critical point. So now similar in case of classical critical point, that all the different physical parameters, susceptibility, specific, relaxation rate, that diverges towards t tending to 0. And as I told you, that due to the presence of these quantum critical fluctuations, of course, the divergence, as I told you, the power laws, the universality classes in case of normal classical phase transitions, of course, those kind of exponent is not going to be valid here because of the presence of quantum critical fluctuations. And till now, there is not that many number of systems by which you can study this quantum critical point, especially the systems which are kind of, which is quite, which is kind of, there is not much disorder, okay? So that's why these kind of systems are very much interesting. Not only that, because of the presence of this quantum critical fluctuations, you would see some kind of non-Fermi liquid behavior in different systems. And of course, theoretical description of those kind of states are rather challenging. So thus, what we have understood is that what is the difference between a classical critical point and a quantum critical point. So now what you can see is that not only the other thing, but also what you can see is that sometimes before reaching to the quantum critical point, some system can show some kind of exotic states that include superconductivity as well. And it has also been seen that the quantum critical fluctuations promotes the superconductivity in some unconventional system. So that is why these kind of systems, which is associated with the quantum critical point, is very much of special interest nowadays. So if we understood that, we can also see that this corona situation here, we know that some of us are actually formulated that, okay, after the first wave, we should get some quantum critical point, which means that there is no cases of corona at all. But it didn't happen. Still, there were some cases, and then the second peak start. But probably, hopefully, you are expecting that there will be a quantum critical point when there is no corona in the future. Okay, so jokes apart. So now what we have understood is that you need to have some kind of competing exchange interactions in order to achieve this quantum critical point. Okay, so there are several mechanisms by which you can go to a quantum critical point, but today I'm going to talk about only those which are relevant to this today's particular topic. So to start with, let me tell you a few things about these 4F based systems. So we already know that the orbitals are rather quite local in case of 4F based systems compared to the 3D or the 5D system. So this more locality or the more local character of these moments actually give rise to strong correlations. Okay, so now what are the things that happens in these 4F based systems, because of which one can estimate or one can expect some kind of quantum critical behaviors? So there are two types of interaction, competing interactions that are present in hemifermionic system. One of that is actually Kondo interaction. So we already know that what happens is that the local moment, the 4F local moment, can interact with the conduction electrons, because we are talking about metallic systems. So what happens at a lower temperature, the local moment couples with the conduction electron and forms some kind of many body singlet type of states. And what happens is that at further low temperature, sometimes the conduction electron can completely screen the moment of the local moments. And as a result, what happens is that even though you have a finite moment in the system, but the system does not show any long-range magnetic ordering at very low temperature. And that particular state is called as the Fermi liquid type of state. Of course, there is a one-to-one correspondence between the Fermi liquid state and Fermi gas. But of course, here, to incorporate the correlation between the electrons, you have to consider that the fermions are rather heavy compared to the Fermi gas system. So what we understood is that this Kondo interaction always try to reduce down the long-range magnetic order. So there is another type of interaction that are present in 4F heavy fermionic systems, is that this RKKY type of interactions. So that interaction is nothing but the interactions between the 4F moments. And you can easily consider that the more the RKKY type of interactions, more you have the possibility to stabilize the magnetic ordering at a higher temperature. So these two interactions are rather competing with respect to each other. And thus one can easily help, one can really think that, okay, of course, the competition of these two can give rise to something that we are expecting. And there is a famous phase diagram that is done by Doniak. As you can see here, along the x-axis, you have the exchange interaction that is being tuned by pressure or magnetic field or some other non-thermal parameter. Along the y-axis, you have the temperature. So we know that what is the behavior, how the Kondo exchange interactions are behaving if you change the exchanges. And we also know that how the RKKY type of exchange is actually behaving depending on the exchange interactions. So what you can see is that at lower values of J, you have dominating RKKY type of interactions, but you have less Kondo type of interactions. So which means is that at low J values, the long range order would be more possible to get stabilized. But as you are increasing the J, you can see that after a particular point, the condo wins over the arc-Y type of interactions. And then, of course, because of the enhancement of the condo interaction, it is going to try to reduce down the long-range magnetic ordering. And eventually, you can go to a quantum critical point. And of course, around that quantum critical point, because of the strong quantum fluctuations, you can expect some non-Fermi liquid behavior. Such a Fermi liquid behavior won't be possible to see in that particular region. So you have here the competition between condo and arc-Y. Let us figure it out some other way by which you can reduce down the order. So that is nothing but frustration. So just to give you an idea about the idea of frustration is, you can consider a triangular lattice. And if you consider a Ising spin, which means the spin can be either up or down, if they are arranged in the corners, and if the interaction between them are antiferromagnetic type, then you know that the third spin would be really frustrated. It doesn't know in which direction it has to align itself. And in this situation, what happens is that the ground state has a huge number of degeneracy. So you can see for a certain, for this particular simple example, you have 6 different spin configuration of the spins that all have the similar amount of energy. And thus the system doesn't know in which direction or in which configuration it should align itself. So as a result, there won't be any long-range magnetic ordering, even down to very low temperature. And this kind of state has been coined as the name of spin liquid type of states. And these are exotic states of matter where huge correlations are there between the spins, but the spins are unable to kind of arrange in a particular regular manner, even down to t = 0. Okay, so now what we have seen is that different ways of finding a situation where you can suppress down the long-range magnetic ordering. So now the point is, what happens if you have a system where you have condo, arc-Y, and frustration? So that immediately tells you that, okay, then you are thinking about a system where you have frustration in metals. Why I'm kind of surprised about that, because most of the studies in the last several years, while people talking about spin liquids or frustration, they mostly talk about insulating systems. But here we can easily figure it out that to have a condo and arc-Y type of interaction, you need to have a lot of conduction electrons. So we will be talking about a new type of situation where you are dealing with a system where it is a metal, as well as you have frustration, as well as you have these other 2 kind of interactions. So this question arises, and afterwards, a very complicated phase diagram has been proposed by theory, as you can see here from the reference, is that along the x-axis, you have this condo coupling. Of course, it is in the unit of arc-Y type of interaction. It is just the ratio of it. And along the y-axis, you have quantum fluctuation. So how you can promote quantum fluctuation? Either you can kind of incorporate more frustration in the system. That is one of the way. Other ways that you can reduce the dimensionality of the system. But for our case, in this particular case, we'll be considering that that particular axis is nothing but the strength of the frustration. Okay, so now what you can see in this phase diagram, there are a lot of phase transitions are happening, a lot of quantum critical points are being proposed for this phase diagram. And also not only that, but also at a regime at where you have high quantum fluctuations, you can expect some kind of spin liquid type of behavior as well. Okay, so now the main goal for our study that we'll be discussing in the coming slide is that the kind of genetic phase diagram that I have shown in the beginning about the quantum critical point, whether the same genetic phase diagram is also valid where you have frustration also. Okay, other than the condo and arc-Y, if you have frustration, whether the incorporation of frustration can change the genetic phase diagram of this quantum critical point. Okay, so after getting this idea, the next step is to really look for some system promising candidate which can give rise to this kind of physics. And for that, we have chosen this cerium, palladium, aluminium. Of course, cerium is, as I told, it is for a system, and that is the main kind of source of magnetic moment in this particular system. So, of course, this particular system is a metallic system, and you can see that the cerium moments are arranged in a way that there are corner shared triangles, and that particular type of structure is called as the Kagome type of lattice, and that is also a frustrated lattice. So we have a metallic system and we have the cerium moments, which are also 4F, that is also arranged in a frustrated type of structure. So now we know that, okay, this might be a interesting system to start with. So now, not only this, but also what we have realized is that there are few candidates, not much, that on which such kind of frustrated lattice with cerium moments are there. There are few, but this system is a bit special. Why it is so special? Because this system has been around for a long time, rather, but it has drawn nowadays it has drawn a lot of interest because of the phase diagram that I have shown you earlier. So it is very special in the sense that it is highly tunable. So now you can see here, so it is highly tunable by the application of magnetic field. You can suppress down the long range magnetic ordering and get some different type of states. It is very much susceptible to pressure as well, hydrostatic pressure. You can suppress down the ordering. Not only that, but chemical pressure also, by doping also you can suppress down the ordering. So there are huge possibilities. As I told you, our main idea is to really look for the difference between a system where you have only RKKY and condo and a system where you have RKKY, condo and frustration. So we need to figure it out different ways to study this quantum critical behavior, whether it is different or in the same line with the conventional quantum critical systems. Okay, so of course the work on doping and magnetic field is going on. Today I'll be kind of concentrating on the situation where we are studying cerium, palladium, aluminum, which has a long range magnetic ordering at around 2.8 Kelvin under pressure. What is happening here? Okay, so to go further detail, so just let me clarify one thing to you, is that in a insulating frustrated system, as I told you, that frustrated system and spin liquid behavior, these are mostly been studied in insulating system. And there what happens is that you see that the Curie-wise kind of constant that is much higher than that of the ordering temperature. And which means is that Curie-wise temperature, the system wanted to order at the Curie-wise temperature, but because of the presence of frustration, the system orders at a further lower temperature. And the state between that is kind of spin liquid type of state. Okay, but now you can see is that while so this particular kind of scenario might not be that much valid where you have condo and RKKY and frustration, because the fact is that you know that this Tn in case of frustration in a metallic system is not only driven by frustration only, but also it can be driven by the condo and RKKY type of interaction as well. So thus, in that case, it might be really difficult to figure it out, this spin liquid type of regime. Okay, so to do that, what people have suggested is that here in the right hand side, you can see the M over H data for cerium, palladium, aluminum as a function of temperature. So just follow the red curve. So you can see that there is a hump-like behavior of the magnetization at a characteristic temperature that is called Ts. And below in this inflection point, you have this long-range magnetic ordering. So not only that, they have also found out that at around this Ts temperature, there is a huge accumulation of entropy above the long-range magnetic ordering. So thus, what you can consider is that the regime between this Ts and Tn is actually the regime where your frustration is actually more visible, or the systems is actually in the spin liquid state. Because the system where you know already that the accumulation of entropy happens at around the ordering temperature, but the system in this particular system, the ordering temperature is at much lower temperature. Thus, that is the regime where the system is actually in the spin liquid. So, so far so good. So now let us proceed to the experimental data. So we have utilized a local technique that is called muon spin relaxation or rotation technique. So of course, I do not have much time in order to explain everything about these techniques. But what I can say is that we are dealing with these muon particles, which has a finite spin half, and it is plus positive muons you can consider. So now what we do is usually that we usually just inject these muons in a particular system. And what happens is that the muons comes to rest within the system in a interstitial position where it finds the lower potential within the crystal itself. And what happens is that since the muon has a finite spin, So it can really sense the local field around that particular muon site produced by the magnetic elements. So what will happen is that if you are in the long-range magnetically ordered state, so the muon is going to feel a local static magnetic field. And since muon has a spin, so it will start to precess around the local magnetic field. And the precession frequency is nothing but proportional to the local field that the muon is experiencing. So now if you plot the muon depolarization function as a function of time, you can see this kind of oscillations in the long-range magnetically ordered state. So this oscillation is nothing but the precession oscillations of the muon spins. Okay, if you take the Fourier transformation of it, you will get actually the local field that the muon is experiencing because of the local moment that are arranged around it. Okay, so now if you plot this particular frequency or field as a function of temperature, you can get an idea about the nature of the order parameter in the long-range magnetically ordered state. Okay, so not only that, but because of the fact that it has a not only that, but also if you just consider a situation where you are in the paramagnetic state, where the system is not yet into the long-range magnetically ordered state, you see some kind of exponential relaxation of the muon polarization. And from there, one can estimate this lambda that is nothing but the the relaxation rate. So this lambda over t, this particular parameter is actually proportional to the imaginary part of the dynamical spin sensitivity. So which means by probing or by utilizing this lambda over t, you are actually probing the electron spin dynamics in the system. So needless to say, you can see in this particular figure that this lambda over t as a function of temperature, you can see there is a diverging behavior. As I told in the beginning also, for classical second order magnetic phase transition or quantum phase transition, you would see some kind of diverging behavior towards the ordering temperature, and lambda over t is also behaving the same in a system, behaves in the same manner. Okay. So there is another kind of way to do
you have 5 more minutes.
Okay, sure. Yeah. So one can also estimate the precise determination of the magnetic long range ordering by doing IISER as well. Okay. So now let us proceed a little bit quickly. So you can see that this is the data at ambient pressure for cilium, palladium, aluminum. So in the inset, you can easily see that in the ordered state you have oscillations. So which further kind of tell you that, okay, you have this long range magnetic ordering. And also what we have estimated, or we have calculated this, or this lambda over t as a function of time. And you can see this divergence behavior towards the long range magnetic ordering. So not only that, one more point I would like to point out is that, as I told, so the relaxation behavior follows this exponential term, right? And you can see what we have seen is that to deconvolute the spectra, we need to incorporate the effect of the stretched exponential, that is beta. Okay, so what we have seen is that below a characteristic temperature T star, the beta is actually deviating from 1. And this T star found, we have found out that this is nothing but very close to the TS, where we have seen the hump in the magnetization data as a function of temperature. So we are coming to that point later also. So now what is happening as a function of pressure? So we have seen that we can suppress down the magnetic ordering down to a quantum critical point, and the quantum critical pressure is nothing but 0.92 GPa. Okay. So we have of course seen that how the magnetic state is evolving as a function of pressure. What we have seen is that the nature of the magnetic state remains the same with increasing pressure. So now let us see what is happening to the dynamics of the system. To understand that, we have to plot this lambda over t as a function of temperature. So we are just now considering still in the place where still we have the long range magnetic ordering. So we see this divergence of lambda over t towards the long range magnetic ordering temperature. So now let us see the pressure regime where you have no long range magnetic ordering, that is above the quantum critical point. So what you can see is that even at a pressure which is 1.62 GPa, which is much higher than that of the quantum critical pressure, 1.75 times higher than that of the quantum critical pressure, you see some critical divergence of this lambda over t. And that made us surprised that indeed there is a huge difference between a system where there is no frustration but quantum criticality, but is and with respect to a system where you have quantum criticality along with frustration. So as I told you, said without the frustration, this is usually the generic phase diagram. You suppress the ordering, you have this quantum critical point. Around that, you have this quantum critical behavior. But what is happening with the incorporation of frustration is that we do not have any quantum critical point, but rather a quantum critical phase. And because of the incorporation of frustration. So we have seen that this extended quantum critical phase in case of a system where you have Kondo, RKQI, and frustration that are coming to play. So just one more thing is that, as I told you, this T star, there is another characteristic energy scale, that is T star, where our beta was deviating from 1, and that matches with the hump below which we have this spin liquid type of behavior that I have shown in the previous slide. We have also tracked down this as a function of pressure as well. What we have seen is that it is exactly matching, the pressure dependence of T star is exactly matching with respect to the pressure dependence of this TS. And that further indicates that in that particular high pressure regime, below the characteristic temperature T star, you have spin liquid type of behavior. And combining these two, what we have found out is that that around that particular pressure range, of course, you have critical behavior, quantum critical behavior, but also this particular range of pressure is also going to give you the idea about the fact that you have critical spin liquid type of behavior in that extended quantum critical phase. So finally, what I would like to conclude about saying is that according to the expectation, or what we have started with, is that whether any differences can we get between the situation where you do not have any frustration and also the situation where you have any frustration. We have indeed found a drastic difference. We have seen an extended quantum critical phase. Not only that, we have also got the evidence that below a particular characteristic temperature, the system shows a critical spin liquid type of behavior in that full extended critical phase. And thank you for your kind attention.
Thank you, Dr. Mayukh, for a very nice talk. So now Shibro has a question. Yeah, Shibro.
Hi, thanks for the nice talk. Do you know what the resistivity looks like in this phase which does not have magnetic order to the lowest temperature?
Yeah. So while I think, let me just go back. Yeah, I think if you go through this particular paper reference, maybe it is a bit hazy to you. So they have done resistivity. Of course, they have seen also this non-Fermi liquid behavior around that region. So it is not at all following this T-square behavior as expected for a Fermi liquid.
Okay. Can I just ask a
short question? Go ahead.
Okay.
Yes.
So the other question is, what is actually this magnetically order nature of this magnetic order at low pressure?
Yeah, at ambient pressure, it shows a antiferromagnetic type of incommensurate antiferromagnetic order.
It's still collinear.
So maybe I can, if I'm allowed, let me just show you the phase diagram. The magnetic structure. Yeah, as you can see here. So it has been done by neutron scattering. You can see that in the AB plane, there is this antiferromagnetic type of kind of spin alignment. Along the C axis, you have this incommensurate type of modulation of the magnetic moments.
I see. It's okay. Thanks.
Okay. There is a question in the chat window. Dr. Sri Dhanashekar, he is asking, is there any structural change under pressure at low temperature?
Yeah, truly speaking, that there is, we have not really studied the structure as a function of pressure, but as I told, so we have seen smooth evolution of all the physical properties. As I told, the nature of the ordering, everything is quite smooth. So in that sense, it is probably okay to consider the fact that there is no change of structural phase in this cerium palladium.
Shovan, yeah, go ahead.
Thanks a lot for this wonderful talk. So I have a question, as I'm a bit confused with the T star temperature. So can you please how do you define the T star here, and how does it relate to photo temperature?
No. Sorry, maybe I mean that went.
So this is not the lattice contour temperature. This is a complete.
No.
Okay.
So yeah, let me just tell you that from the magnetization as a function of temperature. So what they have seen is that there is a hump at IISER temperature scale. Not only that, they have seen that there is a huge entropy accumulation at that temperature. So which means is that you know that you would expect that at the ordering temperature you have a lot of entropy accumulation. So from there they have concluded is that or they thought that this TS temperature scale can be a good indication of the frustration in the system. Maybe the system wanted to order at that TS temperature, but it was unable to get ordered because of the frustration, and then eventually it went to a ordering below the ordering temperature. And T star is actually this temperature where the system shows this hump-like behavior.
Okay.
And that is nothing but I mean. So as I told you, so in the paramagnetic state, this muon depolarization curve shows some exponential behavior. But what we have observed is that it shows some you need to employ some stressed exponential. So it seems that you have multiple relaxation channels actually. And that kind of the deviation from one of this beta is actually denoted by T star. And with pressure also we have seen that this T star, the behavior of T star and TS, you can see here. Our data is actually the yellow circles, and this TS is nothing but these squares, and you can see the pressure dependence of both of the energy scales are exactly following similar way. So thus we are expecting that in that high pressure regime, of course we have quantum critical fluctuations, but also this is some kind of a critical spin liquid type of behavior.
So I might have one more fundamental question, if I may ask.
Sure.
Okay.
I mean,
I'm sorry.
Yes, no, if Professor Thamizabel allows, yeah.
Yes, go ahead.
Okay. This is a rather fundamental question regarding the Doniach diagram that you showed. So, so my understanding, you may correct me if I was wrong. So, so my understanding on the Doniach picture was that when these competing interactions cross each other, so that's basically the crossing point of the contour and the RKKY interaction, it is actually at that point where you would eventually land up to the quantum critical point. Is it a very... can I take it as a schematic error, or is it?
Yeah, schematic. You can consider it a schematic error. Yeah.
Okay.
Yeah. But also, needless to say, I mean, let me just tell you that, I mean, you know that in a lot of systems where the contour temperature is rather high, but still you would see some long-range magnetic ordering in the low temperature. So it's not always the fact that the conduction electron will completely screen the moment. So it can also leave some moment unscreened, and because of which you can get some long-range magnetic ordering even well below the contour temperature.
Okay.
So does I think maybe in that sense, maybe this is okay in that sense. So yeah, it is not exactly at a particular point. Yeah.
Okay.
Thank you.
Thank you,
Dr. Mayukh Mazumdar.
Hi, can I have a question? I don't. There is no hand raise on my Zoom. I don't know why. Can I have a small question?
Yeah, quick question. This is the last question. Yeah.
Okay, sure. Small. So here you are studying this Kagome type system, right? And here we already like system itself is like frustrated. Magnetism is sport. And in your system, we are seeing like out of plane magnetism. So question is, how can we? I mean,
can you repeat? Can you just repeat? So in my system, what you mean?
Okay. In the with reference to your basic magnetic structure, which you showed, right?
Okay.
Last, yeah. So question is, right, your magnetic moment is out of plane. So what gives rise to frustration here? And second, this system is a Kagome lattice, right? And you already have a flat band kind physics where, so can you have a comment on that as well?
Okay, so first question first. So as I told, as you told, so of course, let me just go back to the, So first of all, the point is that of course, the system is going to a long-range magnetically ordered state. But so in this particular system, the frustration is not enough, or there are some other exchanges that are coming into play. As I told you, you have RKKY type of interaction, which may stabilize also the long-range magnetic ordering. We do not know that which exactly is actually responsible for the order state at low temperature. But still, because of the presence of these frustrated Kagome lattice, you still have this frustration that is present. Does it answer to your question?
Yeah, it's a part of. Okay, thank you.
Yeah, thank you very much once again. So with this, we have come to the end of this session, and let's thank all the speakers. Now over to the organizers. Yeah, Pratap.
Okay, thank you, Dhanvir, for chairing the session, and I thank all the speakers for very nice presentations. So we come to the end of today. Tomorrow, the session will start with regular parallel sessions as usual at 9 o'clock. And both the sessions will be started on Zoom 10 minutes before the start of the event. Okay, so good night and see you tomorrow.